We say that probability of getting head is 0.5 when we toss a coin. Let's assume we have a coin with two sides, head and tail, and we toss this coin 4 times and we get 2 heads, 2 tails. So we can get a ratio of number of heads to number of trials. Number of heads is 2 here and we tossed 4 times. So number of trials is 4. Hence the ratio is 2 by 4 equals to 0.5. Perfect. Makes sense. Probability of getting head is also 0.5 as we say. But in reality we can get 1 head also. And this ratio becomes 0.25. If we get 3 heads, ratio becomes 0.75. Let's toss this coin 5 times. We can get this ratio as 0.4. We can get this ratio as 0.6 also. We toss 10 times. This ratio may become 0.7 or 0.4. Still we say that when we toss a coin, probability of getting head is 0.5. The reason lies in the empirical or statistical definition of probability. In concept of empirical probability, when we do any random experiment like tossing a coin or throwing a die, if in n number of trials an event E happens m times, then the probability of the happening of the event E is given by the ratio m by n only when n is a large number, or we can say when n tends to infinity. So when we toss a coin, we can write this statement like this. That means probability of getting head will become the ratio of number of heads to the number of tosses only when we toss the coin a large number of times. Hence, to conclude 0.5 as the probability of getting head, we need to toss the coin a large number of times to see this ratio reach the probability value 0.5. Here we talked about tossing the coin 4 times, 5 times and 10 times. We can toss a coin 20 times or 50 times also, but how much large number of times we can toss? Obviously, we don't want to toss a coin all day long to count the number of heads in 1000 or 5000 or 10,000 number of trials. So we can do a simulation here in Python. NumPy module is imported here in this Python script as np. This is the sample space, a list containing two face values of a coin, h for head and t for tail. At first we want to toss the coin 10 times. Number of trials is 10. Then we need to write this line of code. From random submodule in NumPy library, we need to call choice function. Pass this sample space, size equals to number of trials, replace equals to true. Use print command on it. Run the script. It tosses this coin 10 times and we get 1, 2, 3, 4, 5, 6 heads. Every time we run the script, it tosses this coin 10 times and we get heads and tails here. Now we want to see the ratio of the number of heads to the number of trials when it tosses the coin. To do so, we need to do equality check with h here, pass it to sum function. Divided by number of trials, that means number of tosses. Run the script. We get ratio of number of heads to number of trials. Every time we run the script, it tosses the coin 10 times, then calculates the respective ratio values to show here. Now let's increase the number of trials. every time it will toss the coin 30 times. Run the script. We get the ratio value 0.566. Run it again. We get 0.266. Run it again, 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 again. We can see when the number of trials is 30, the ratio values are fluctuating a lot. Very few times it is nearby the value 0.5. Let's increase this number to 1000. Run the script. We get the ratio value 0.478, 0.503, 0.488, 0.483, 0.488, 0.521, 0.519. Now we can see ratio values are more close to 0.5 and less fluctuating. Let's take number of trials 5000. Run the script and we can see ratio values are quite nearby the value 0.5 and very less fluctuating. We can visualize it by creating an animated plot here. Import matplotlib.pyplot as plt from animation submodule in matplotlib module. Import func animation function. Instead of a specific number of trials, we will take a numpy array here, np.arrange, containing sequence of numbers starting at 10, stop at 10,000. That's why we need to write this number 10,010 as we take the step length 10. We will take an empty list ratio equals to empty square brackets. To append ratio values in this list using a for loop, for I in number of trials, provide indentation here. Remove this print command. Write ratio dot append. We need to write I here. Initiate a plot specifying X label, Y label, X tick locations and Y tick locations. Set X limit and Y limit. We will have two lengthening lines in this graph. First one will be a red line representing the ratio line. Second one will be a horizontal line representing the probability line at 0.5. We need to declare three empty lists here for appending X coordinate values, for appending values for the ratio line, and for appending value 0.5 for the horizontal probability line. Then we define a function, let's take it as anim function, for appending values in these three lists and for plotting the two animated lines accordingly. Call func animation function, pass figure, which we have declared here, comma, function equals to anim, comma, frames equals to num dot sort, sorted number of trials sequence, comma, interval equals to 10. Assign this to a variable animate plt dot so. We are done. Let's run the script. And it's throwing an error because we need to write here hi. Let's run the script once again. Let's maximize it. And we can see this animated plot. Red line is the ratio line and blue line is the probability line at 0.5 here. Every time it is tossing the coin a certain number of times, it is calculating the respective ratio of values to plot here as the red line. The number of tosses, that means number of trials, is increasing by 10, and the ratio line, that means the red line, is lengthening accordingly. Initially, we can notice when number of trials is less, ratio of values are fluctuating a lot. Consequently, this ratio line is also fluctuating. Probability line has been plotted here to lengthen constantly at 0.5. Although ratio line is fluctuating, but it is always trying to stay nearby the probability line and crossing it frequently. Gradually, we can notice ratio line is lengthening forward by staying very much close to the probability line. It is less fluctuating now. Because as the number of trials is becoming larger and larger, respective ratio values are becoming more and more close to the value 0.5. When the number of trials is quite large, this ratio line tends to merge with the probability line. Here this plot shows how ratio value tends to the value 0.5. Consequently, ratio line tends to merge with the probability line till the number of trials gradually becomes 10,000. If we increase the number of trials to 20,000 or 50,000, this ratio line will almost merge with the probability line. Goodbye and have a good day.